All right, welcome back. So our next topic is something called Rules of Inference. And Rules of Inference are the building block from which we're going to be able to construct logical proofs. So let me give you an example of how we can use Rules of Inference. Suppose I make the proposition, if it's sunny, then I go for a run. And then I tell you it's sunny, and I say therefore I go for a run. And we can ask the question, is this succession of statements logically valid? In other words, suppose that if it's sunny then I go for a run is a true proposition. And suppose that it's sunny is also a true proposition. Given that, can we conclude I go for a run is also a true proposition? And that's a useful thing to be able to do, right? To know that the truth of a set of statements leads to the truth of a following statement. And so let's write this in the language of propositional calculus. So let P be the proposition, it's sunny. And we're going to try to use the smallest propositions we can. We could make P the proposition, if it's sunny then I go for a run, but that's a big proposition. We want to put things in as small pieces as possible. So P is the proposition, it's sunny, and let Q be the proposition, I go for a run. Now what's the first thing you should do when you're working with proofs like this? Make sure you've written propositions. It's sunny. Is that a declarative statement with truth value? Yes. I go for a run. Is that a declarative statement with truth value? Yes. So far so good. We have propositions. Let's rewrite this argument using these propositional variables. If it's sunny, then I go for a run. That's written as if P, then Q. If it's sunny, then I go for a run. And then we're told it's sunny, which is proposition P. The therefore part, we draw a line, just like when we're doing a calculation, adding numbers together. And then the conclusion, I go for a run, that's proposition Q. So this wordy argument over here with 4 lines to it can be written in the language of propositional calculus with this nice equation-like structure. P implies Q, P, therefore Q. And we can ask, is this valid? Rules of inference are rules that will let us know when we're inferring something correctly from other things that we know to be true. And there's a table in the text, it's on page 59, common implications and equivalents, that show us how we can argue things logically. So there's a rule called detachment. Given that P implies Q and given P, we can conclude Q. And that's exactly what we have right here. P implies Q and P, and therefore Q. This is detachment. And knowing the rule of inference called detachment, we can conclude this argument is valid, and therefore this argument is valid. All right, this is a useful way to prove things. Suppose, for example, we have 26 propositions, A, B, C, up through Z. And we know the following statement. We know A, and we know that A implies B, and we know that B implies C, and C implies D, and Y implies Z. And we claim that all of this implies Z. Okay, let me write this out in this equation-like form. We're given proposition A implies B, B implies C, C implies D, and we can't normally do dot dot dots, but I'll do dot dot dots for now. We'll understand that this is continuing in the obvious way. Y implies Z, and we claim that we can conclude Z. And we want to prove that given these, we can conclude Z. Well, we could do this with a truth table, right? We could list all the possible values of A and B and then show that in all the cases where these are all true, Z turns out to be true, and in cases where any of these are false, Z may turn out to be true or not. That's a big truth table, right? We can do this using rules of inference. For example, we know A, and we know that A implies B, and I'm going to number these, by the way. We know A, and we know implies B, and therefore we know B. And we know B implies C, and therefore we know C, and so on. Okay, I'm going to write down reasons why we know these things. Why do we know A? That's a hypothesis. Right, when we write A, we're saying A is true. So this is hypothesis 1. And we know A implies B, that's a hypothesis from 2. And now we claim that B is true. Why is that? That's detachment. And it's detachment of this and this. Alright, and we know B implies C, that's a hypothesis. And given B and B implies C, we know C, that's detachment of this and this. I'm being a little sloppy in the notation here, I'm going to clean it up in a second. Alright, so we can use these rules of inference, and we'll take another look at them here. Detachment, given that P implies Q, and given P we conclude Q. Indirect reasoning, given that P implies Q and Q is false, we can conclude not P. Disjunctive addition, P implies P or Q, right? If P is true, then certainly P or Q is true. Doesn't matter what Q is. Because for P or Q to be true, we only need P to be true, and it is. Chain rule, if P implies Q and Q implies R, then P implies R, and we can prove that pretty easily, but we can also use it, and so on. So these are very powerful rules, and we're going to spend a lot of time using these to prove different things. So let me give you another example, and we'll work this one out a little more carefully. So here's the setup. If you send me an email, then I'll finish my homework. If you don't send me an email, then I'll sleep early. If I go to sleep early, then I wake up refreshed. And therefore, the conclusion we're claiming, and these 3 dots mean therefore, therefore if I don't finish my homework, I'll wake up refreshed. So this is a logical argument. We want to know if it is valid. Logical argument, logical thinking or not. If you send me an email, I'll finish my homework. If you don't send me an email, I go to sleep early. If I go to sleep early, I'll wake up refreshed. Therefore, if I don't finish my homework, I'll wake up refreshed. And if you think about this, you can probably kind of convince yourself that it's true, but we can show this pretty rigorously as follows. So let E be the proposition. You send me an email. And don't do this at first, write it out. Let E be the proposition, you send me an email. Let H be the proposition, I finish my homework. Let S be the proposition, I go to sleep early. Let R be the proposition, I wake up refreshed. So let's rewrite this argument using these propositional variables. If you send me an email, then I finish my homework. That's what this first sentence says. If you don't send me an email, I'll go to sleep early. That's what the second sentence says. If I go to sleep early, then I'll wake up refreshed. That's the third sentence, and the conclusion is, if I don't finish my homework, then I wake up refreshed. So showing that this is logically valid is the same thing as showing that this is logically valid. And we can do this using rules of inference. Okay, so here's a proof. And here's the way I'd like you to do these proofs. Well, first thing we're going to do, all we know is this, this, and this. We get to assume these. Because this argument is saying, assuming this, this, and this are true, is this result true? Is this conclusion true? All right, so we get to assume this, this, and this are true. And you kind of look around at this and you try to figure out things that you can do. Well, I see a chain rule right away. I see this implies S and S implies R. So let's put those together. So here's what I'm going to do. I'm going to say not E implies S. That's a hypothesis. And I'm going to label the statements of my proof rather than the statements of the argument I'm trying to prove. So statement 1 is that not E implies S. The reason that's true is because it was given to us. It's a hypothesis. Statement 2 is that S implies R. That's also a hypothesis. Okay, statement 3 is going to use the chain rule and say not E implies R. So look at your rules of inference, and down here is the chain rule, and you can see that that applies clearly to this situation here. So this is the chain rule applied to statements 1 and 2. So now we know not E implies R. Well, we know that E implies H, and we'd like to show that not H implies R. So how can we turn E implies H into something? This is the only statement including H. How can we turn this into something that has not H? Look at your rules over here and see where you get a negation on the right side. And all the way down here at the bottom is a contrapositive. P implies Q is equivalent to not Q implies not P. And that's our idea here. So let's start off and write down E implies H. That's the hypothesis. And apply the contrapositive to that, and it says not H implies not E. And that's the contrapositive applied to statement 4. Well, now we know not H implies not E, and we've already shown not E implies R. We can put those together and say not H implies R. And that's a chain rule applied to 5 and 3. Not H implies E, not E implies R. Put them together, not H implies R. And hey, guess what? That's what we were trying to show. So we can say QED, which was what we were asked to demonstrate. And we've just proven that these three things imply not H implies R. So this is a valid logical argument.